So a quick introduction to where we're from. The MSSL, Millard Space Science Laboratory, is the Department of Space and Climate Physics of University College London. We are actually not situated in London. We are situated in a little Victorian mansion in the middle of nowhere in the Surrey countryside. Lovely when you get in, but difficult to get in or get out, especially when it's snowing us out. We do have a lot of heritage with space plasma instruments, and that's where we come in on the Discoverer, where we are providing one of these instruments. Lots of missions to planetary magnetospheric environments. Solar Orbiter, that's the instrument there, awaiting delivery, awaiting launch in February. So that's going to be an exciting time. And of course, Discoverer, we're about to hopefully deliver within the next few months and looking forward to the launch in August. Where Discoverer comes in is part of our miniaturization program. That's our Solar Orbiter single head. Your CubeSat, our conventional instruments were never going to fly. That's where we set out on our miniaturization program. Lots of different prototyping, and eventually we've ended up with the ion and neutral mass spectrometers that was flown on QB50 and a modification to be flown on Discoverer. I'll go through, talk about different aspects of the space instrument. In order to get information about the local in situ environment, you need something that conditions that plasma. This is more general, so even if it was a telescope, your conditioning element is your optics, and eventually then your conditioned quantity is then detected by a detector, converted into electronic signal, and this is a classic instrument in general, but space instrument in particular. And I'll mostly be focusing on that, but as I go along, I'll also be talking a little bit about detection and signal processing. For this, what I've done is it's a wide field. When it comes to plasma diagnostics, there's a huge plethora of techniques and technologies. So all I could do within a half an hour is to focus on, and QB50 and Discoverer are very good examples. So I'm focusing mostly on that, and that's where I will try and focus, spend a little bit more time on those elements. Okay, so that's what we're dealing with on QB50. So in the first instance, your information conditioning element is going to have to talk about what the requirements are. And this is what we are trying to study on QB50. We got an orbit somewhere in that region, and those are typically the ions that you're going to be looking at and the neutral particles. So this kind of defines at least what sort of densities we're going to be looking at. There are other aspects which will come to later, like the velocity, but largely at around 380, we're going to be dominated usually, as everybody knows, by atomic oxygen, but the instrument will try and attempt to look at some of the lower species as long as it's not buried in the noise. And hopefully, at least on Discoverer, these low quantities will potentially stand out because we got additional capability in there. So in terms of requirements definition for scientific requirements, you also have a number of other aspects that you got to deal with in a space instrument. There are engineering drivers. You're going to be restricted with mass and power resources. Of course, depending on the orbit, you're going to be affected by, if you're lower, it's going to be a much larger density you're going to be dealing with. If you're higher, lower density, sometimes you are. And in fact, even on Discoverer, we're going to be gradually going down, and you're going to be dealing with 2 or 3 orders of magnitude, for example, just for flux, as well as you saw in that graph, different particle types are going to appear and disappear. You got to worry about things like thermal, vibration, etc. So several requirements in addition to just the science. So when designing a space plasma instrument, there are a lot of aspects that need to be looked at. And in the way we are able to achieve this level of miniaturization here is by trying to restrict the science focus. If you're going to Mercury or if you're going to Pluto or something like that, it's a different story. You need that large dynamic range. But here, we know exactly what the requirements for Discoverer are. So we try and focus and tune the instrument so that you can then remain within the mass and power resources, but still get what is required. In this case, it's an input required primarily for the aerodynamic demonstration. We will obviously be able to do lots of fantastic science with it, but as far as the requirement is concerned, we want to tune the instrument to mainly be an input for the aerodynamic demonstration. So besides density, what are the other aspects? So you do want to know what the angle the incoming particle is at, because in some cases, in this case, we are trying to do crosswinds and ram velocity direction measurements. And of course, the area is going to drive then how many particles are going to make it into your instrument. And so once you know the area, then you can correlate it with the incoming particles. And of course, you want to know the the variability as the satellite goes through these different environments. In some cases, the velocity is low, in others it's high. So you want to be able to make measurements with a sufficient cadence so that you can split up the information. So this is basically, once you have the requirement, then you go into the actual design of the instrument. And for all of what I'll be talking about, that's the basic equation. This is how we're going to be making measurements of all our quantities using very, very simple, effectively, forces. In the first case, where we're doing energy, it will be the electrostatic force. And I'll go through a whole bunch of different examples and, very simple mathematics. It's all A-level physics. But effectively, it's a measurement of any two of these quantities. And then you know your energy and mass. Or if you know the mass, then you can get the velocity and so on and so forth. So I will be talking through mainly electrostatic forces and a technique called the time of flight. If I do have time towards the end, then I'll try and look at magnetic techniques also. Types of analyzers. You heard about the Langley probes and retarding potential analyzers as one of the examples. The technique is quite simple. You have voltages which you can vary, and the incoming plasma. When that voltage is zero, then all the plasma is collected, and very simplistically, you're doing a current measurement there. As you raise the voltage, then you cut off the energy as you go. If you have an energy distribution that looks like that, where that's energy and counts, what the gridded Faraday cup would do is at low voltages, you're integrating that. As you go to higher voltages, and that's what you're doing, and then at higher. So by taking multiple measurements, and there's several different techniques to be able to then correlate that to a total plasma density. It's not so easy to get that energy breakdown of that. And that's where differential particle analyzers come into the picture. That's an example of a Langley probe that was flown on the Rosetta mission. There are loads of different examples that you can find. The last slide gives references, so there we can go and look for more information. Then you have the differential type, where by applying electrostatic voltages, bend the trajectories, and then by placing a detector here, it's a very specific energy and species that makes it to the detector. So simple A-level equations, you got a parabolic path. Eventually, the deflection is proportional to the incoming energy by charge state in this case. And of course, as you can see, there's no mass in there. So ions of all masses will come to will end up at the same position. Electrons and negative ions will also end up at that same position. So as far as instruments like these are concerned, and a few other examples that I'll be going through further, they are doing energy only, as in E by Q. Quite often there are charge state dependencies. That's an additional level of complication. And usually, I do have an example later, you have position sensitive detectors, so you can actually get an energy spectrogram from that. In some cases, very powerful, because you can get your energy spectrogram without having to vary voltages too much. So that's your planar type. And then the next one. Okay, some disadvantages: that dispersion is nonlinear. So the position versus energy information is nonlinear. So one does need to build that into. So there are some issues like that. But I have a slightly more detailed of the Fonema example later where this technique is used. And then the spherical ones. These are much more commonly used, although not necessarily as powerful as the planar ones. And again, the principle is very simple. You got the centripetal force balanced by the electrostatic force. And once you work out the mathematics, your energy is directly proportional to the voltage applied. So as an example, if it's an electron here, you apply a positive voltage, then what reaches the detector is a very narrow band of energies. And as you change the voltages on the detector, then you cover the energy range effectively. So you sweep the voltage in order to obtain the energy distribution. So the previous one, you have a position sensitive detector. You do not have to sweep these voltages. So there's an advantage there. But there is the additional complexity of having a position sensitive detector. And the other thing is the proportionality constant is driven entirely by the geometry of the instrument. So it's just driven by what radii of the inner and outer hemispheres that you would choose. And loads of different shapes of these spherical devices have been flown. There's the quadrispheric, there's the hemispheric, the tri-quadrispheric, and I think I have an example of the tri-quadrispheric. This was the Giotto fast ion sensor that went on to the Halley's mission, went on to study Halley's Comet. An incoming ion, 270 degrees, and you then have a detector here. If the incoming ion was at a different angle, you ended up at a different position, and that's how you also got your angular information in addition to the energy which came from sweeping the voltages on this. The most popular, at least in space plasmas, is something called a tri-quadrispheric or a top hat analyzer, and effectively it's two hemispheres, very similar. Obviously, it's the same principle as far as energy analysis is concerned. But the nice thing is you got your 360-degree field of view. So very powerful in terms of when you want to study a large volume, you want a 360 degrees. We made some enhancements to this. So this is an example of the bunch of Top Hat family of analyzers that have been flown from MSSL. Cluster Piece that was launched in 2000. 8 instruments were launched, all 8 still providing data. That's the engineering model for the Cassini electron spectrometer. As you know, Cassini, the satellite itself, has fallen into Saturn. These are top hats. We took this, miniaturized it, added some functionality, and that's what we're providing for the Solar Orbiter. And then there are the cylindrical and the toroidal geometries. Obviously, that's where I'll spend a lot of my time. This was a note to say the angular acceptance of these analyzers and all of the analyzers that I'll be talking about is very restricted. So you do need techniques to try and look at a wider field of view where necessary. And this is a good example because I'm also partially using this on the INMS, or at least for ions. And very simply, when you have a voltage here, the electrons that were coming in straight get rejected, as in they get attracted to this field. They do not go through, whereas electrons that were earlier going and hitting that plate are bent through, and then it's the classic electrostatic analyzer. That's an example. That is the flight instrument that was delivered for Solar Orbiter. You can see the deflector plates there, 360-degree field of view. In this case, it is 360 by plus minus 45 degrees, and the other instrument, the other sensor being placed orthogonally means you can do a full sky, a 4-pi measurement with these. We also introduced this, and again, this is something that is, it's a common element that we have implemented in all our instruments, which is an electrostatic tap. So when you change the potential here, the number of particles that would normally have gone through is changed, and by applying enough potential between these two plates, positive potential here, you have less and less going through, so you can actually turn the transmission of the instrument down. Very powerful when you have a very large dynamic range to deal with. So that's a typical performance response of such an electrostatic analyzer. Whether it's the INMS or the top hats, what you will get is that's the voltage. With the proportionality, it's effectively the energy, and that's your angular acceptance. And you can see that it's not linear in one dimension or the other. As different energies go through, then you have a different angular response to be dealing with. So this is very important, and it is actually even more important for the INMS because it's such a directional sensor. Come back to that response slide later. A couple quick notes. Now, once you have the analysis done, then you need a detector, and for most of the detectors that I'm talking about, a microchannel plate or a channel electron multiplier is what is used. A particle, the incident particle strikes the surface. You have a lot of avalanches. You have a lot of secondary electrons because of that potential as the plasma passes through. Every time there's a strike, it doubles, and at the end, you end up with about 10 to the 6, 10 to the 8. If it's a channel electron multiplier, if it's an MCP, then you have different configurations, and you end up with about 10 to the 6. Typically, very rarely, you can push it up to 10 to the 7 gain. And then that signal is measured by a charge-sensitive preamplifier and a leading-edge discriminator, which means as soon as the cloud goes above a certain level, it will give you an output. And what you get is effectively discriminate signals, which are you going to count. And you count that for a fixed acquisition time, change the voltage, and that's how you build up your energy distribution by going through the whole range of voltages that you want in order to cover your energy distribution. And then a couple other aspects. I talked about detectors and angular acceptance. Yeah, all right. So that should cover most of the fundamentals of what's happening in there. So a more specific example, which is the INMS. Again, back to that schematic. The key thing is most of these particles are relatively immobile in most of the environment, particularly in the equatorial belts. You're talking of less than 200 meters per second, 250 meters per second. Maybe in the polar regions, you're pushing it to 500 to 1,000 meters per second. But compared to the spacecraft velocity, it is relatively low. And so what is used in the INMS is the fact that the spacecraft velocity remains the dominant velocity, which means you know the V in the half mv squared. You do a measure of the energy through any one of these techniques that I talked about using electrostatic analyzers. So you got your E, and that gives you your mass. On QB50 and Discoverer, what we did was we effectively just set the voltages to be looking at whatever is the equivalent velocity for oxygen. We have the capability of doing up to 3 masses. So you can either set it for oxygen, molecular and atomic oxygen, and nitrogen, or so within the analyzer you can choose control the voltages so that you can tune your instrument to be looking at any particular species at any instant in time. And then when you're sitting at oxygen, then you can do other things in addition to just doing the energy analysis. And that's where the next kind of Mark II comes in, where we're sitting at one energy, but then measuring the time of flight at that energy in order to get a better resolution. It is a cylindrical geometry rather than a spherical. Advantages and disadvantages to that, but the nice thing is cylindrical geometry is very, very simple relatively. So how does it work? The ions and neutrals, they pass through the aperture. There's your angular acceptance in there. If there are voltages on this and this electrode, meaning the voltages are high enough that ions actually get rejected here through the planar deflection that I talked about. It's only neutral particles that make it through, and with the appropriate voltages applied here, where you drive the ionizer, then the neutral particles get converted into ions, and those ions are then energy analyzed, and you get the density, in this case here, the number of counts for your fixed period, and then doing that energy distribution effectively, the integration of that will give you the density. So on QB50, we did not have resources all the time to do more elaborate measurements, so it only provided us mainly the density. And of course, when both of these are off, then the neutral particles effectively go straight through, and it's the ions that are analyzed, and we do a ping-pong operation of the instrument. I will discuss the energy resolution, the velocities from the orbital dynamics. Can this be used all the time? Not necessarily. Well, it cannot be used all the time, because when you have a very hot plasma, then the energy is much, much higher than the spacecraft velocity. And in several environments, you are traveling much, much lower than in VLEO. In VLEO, it's about 7.7 kilometers per second, whereas very often you will have spacecraft traveling at 2 kilometers per second, with the plasma being much, much hotter. So other techniques have to be applied. And again, if I have time, I will touch on that. Here's an example of in-flight data from one of the QB50. They are supposed to be 3-axis stabilized and ram direction pointing, but unfortunately, this particular satellite, it was the only QB50 satellite that gave us data, so in a way, fortunately. But there is some really lovely physics in here. It was Y-Thomson spinning. So as the satellite went through the ram direction, you got your measurements of the energy distributions every time it went through the ram direction. But the interesting thing is that each of these is a different angle. So now I actually got an energy angle distribution hidden in this, and that actually can be used for getting a velocity measurement. Because with the ram direction, if the plasma has a wind velocity, then you need more techniques in order to be able to make that wind measurement. Whereas here, hoping that when we get around to analyzing this in any more detail, we'll be able to actually measure, extract wind velocity from this. I got about a month's worth of data, so hopefully we'll be able to get some. Very occasionally, you have the luxury of seeing your own instrument in space. And because this was launched from the International Space Station, actually that was a movie, but okay, it doesn't seem to be working. But anyway, fortunately, an astronaut was awake and took a photograph of the 3 sensors on QB50, and that's our INMS, so never tire of showing that. It's very rare you can see your own instrument up there. So, velocity measurement. The QB50 instrument could not do that because it's a simple energy measurement. But what would be needed in order to do that? You're looking at 5 eV. just put in some example numbers here. If you have a wind velocity of about 40 meters per second, you're talking of an energy variation of about 0.05 eV. And the instrument resolution at present on QB50 is over 10%. It's between 10 and 12%. So even the full width at half maximum is 0.5 eV. So that's the reason we cannot make these wind measurements. But on QB50, that's what we want to try to do. We want to see how low we can go and what we need to build in for that. If it was just simple energy resolution changes, it would have to be well below 1%. And when you squeeze the energy resolution down further and further, you affect geometric factors, you affect angular acceptances, so it makes it very, very complicated. So we need to stick to a higher resolution, but instead, we're doing something called the time of flight technique in order to do this velocity measurement. And what does that do? What we've done is effectively taken that QB50 instrument, moved the analyzer back, given a time of flight region. And since, in this case, whatever is reaching here is going to be an ion, either it's been ionized in the neutral particle in the ionizer section, or it's an ion that's coming through. So as long as we hold roughly 10 volts on this, nothing is going to go through. And then we open a small window. In this case, what our FPGA we have been able to achieve is about 12.5 nanoseconds. You open the window for 12.5 nanoseconds, particles pass through, and then you start counting and see what your histogram looks like. The higher the energy, it's going to take a shorter flight time, and then vice versa, lower the energy. So you build that histogram for about 200 nanoseconds and write it away in memory, and then repeat that process for several milliseconds. On Discover, chances are we're going to be running at about 100 milliseconds, where we'll be doing opening and closing of the windows. With the 5%, with the 10% energy resolution, by setting this at a single voltage, we will have roughly that range. This is full width at 10th maximum. You will have between 4.4 and 5.6 eV making it through the detector, and that is a delta of around 300 nanoseconds. So the full width at half maximum would be captured by the 200 nanoseconds, and what we intend to do is either 2 voltages or 3 voltages in order to make sure that we capture the entire distribution. This is the QB50 data, and I have that here. Yeah, so that's the QB50 data, and there you have particles as low as 3.5 eV and as high as 8 eV. So that translates to about 900 nanoseconds. So effectively, by either using, depending on what we see, initial commissioning phases, we would count in multiples of 200 nanoseconds and take those histograms to either cover that range or that range. So there's a lot of flexibility in the way the instrument is commanded to do that. And so that's what we are doing now for SOAR. That's the instrument which is not the SOAR instrument, it's actually the ROAR instrument, because the same set of instruments is going to go into the raw chamber for doing very similar characterization in the chamber, whatever studies that are planned for the ROAR instrument. That's the instrument apertures, and that's a simple Faraday cup. It's set up in the beamline. We do not, unfortunately, have a neutral particle beam, but hopefully ROAR will provide that for testing in here. What we have is an ion beam, so effectively we do all the testing of this with an ion beam. I did show the energy angle graph earlier, and as you saw that depending on the angle you're looking at, the energy distribution is different, so you do need to have very high position knowledge in order to be able to then calibrate out your instrument response accordingly so that it can feed into the velocity measurement. Okay, this is the QB50 instrument. Just a schematic to show that, it's relatively simple, but most of the intelligence has gone into the FPGA in order to be able to do this 12.5 nanosecond, 200 nanosecond, building the histograms, etc. And of course, what we needed to do for that electrostatic gating. So there was a whole bunch of things that we needed to do in order to make that operational. Some hardware, that's the front end with the ionizer, that's the time of flight, the electrostatic gating board. We got hidden behind this is our analyzer with all the detectors, etc. And then that's the digital electronics for the unit. And this is just to demonstrate what I was saying, where you change the voltages on the, okay, I don't have that schematic, but you change the voltage on the hemisphere in order to then make multiple measurements in order to capture that, either that, or depending on what we choose. So, sources of errors. This is going to drive what sort of wind velocity measurements we're going to get. The spacecraft pointing knowledge is very crucial, and I think currently the SOAR goes to about 0.4, 0.5 degrees, so we will have a pretty good pointing, and we would have to build that into the errors effectively in terms of that pointing error. We got other instrument resolutions, the geometric factor, there's contamination elements, there's lots of instrument effects and resolutions that also go into the errors. The larger the width of the window, the bigger the error, because during that opening time, you are going to have a range of energies that are going to come in. 12.5 nanoseconds roughly corresponds to about 20 meters per second, and our goal on Discover is about 250. So hopefully we should be doing much, much better than what our original goal was. This 250 is mainly for the aerodynamics. I mean, obviously from a science point of view, we want much, much lower. We want to go as low as possible. Certain missions in this orbit want as low as 5 meters per second. And yeah, can still be done with this kind of instrument with a longer time of flight. And then there are detection efficiencies, the ionization, the ionizer, converting the neutrals, efficiencies in there. So somewhere in that spectrogram that you saw in this is hidden the velocity and the plasma temperature. So once we have all of these errors and aspects built in, from that we would be extracting one of the features that I actually haven't shown here. We made an additional mod into the instrument. So what you're looking at is two sets of apertures here. And for QB50, because we were going to be going very high and very low, what we did was we made two geometric factors. So one with a larger acceptance, meaning you deal with the larger acceptance. That's the part of the analyzer you would be using for when you're higher up, and as you come lower down, then interestingly, the smaller holes are the higher geometric factor in optics. So it's effectively two parallel chains of this. And what we're doing on Discoverer is making them identical, but with an offset field of view. And when you have an offset field of view, then you can compare this against that and get a measure of crosswind. This was a more recent feature that we have inserted into the instrument, because here you do not need the variable, you do not need two different geometries. The simple reason being there are several other elements in the instrument, like you can go for a whole range of different window widths in order to restrict the plasma through the system. So we've got rid of the different geometries, but we have the crosswind measurement capability instead. Right, okay, so most of what you've heard is already, you know, the velocity because you're using the RAM velocity, and we're making an energy measurement, and that energy measurement is then further being split into 16 channels, if you like. So the 10% that would make it through is then split into 16 channels through the histogramming. But as I said, it's not always possible to get the velocity. So what are the other techniques that are used for these kinds of analyzers where you do get then a measurement? And the other thing to keep in mind is you're always measuring E by Q. So that is important, even though I've not kept it in here, but strictly speaking, I should always be making sure that it's energy by the charge state. If the charge state is different, electrostatically, you're looking at a completely different species. So typically, in that case, you're doing a bunch of techniques. The time of flight I've talked about, but the electrostatic gating is not something that will always work, particularly in a hot plasma. So there are other techniques which can be used. There's the velocity mass selection, and in some cases, magnetic fields. So here's an example of where you are using a magnetic field. It's an E cross B field. It's a very standard instrument that's used for beam diagnostics, that's used for ion beams, for mass selection, etc. And what you're doing is, it's a combination of, with a cross field, one field is moving the beam in one direction, the electrostatic field is moving it in the other direction, and with a small set of apertures, by using a permanent magnet where the B is known, you change the voltage and you will have a whole different velocity. So that's some of the maths, and as you can see, the velocity is proportional to the applied electric field divided by the magnetic field. This is known, so you let a different velocity by changing the voltage on the field. And of course, that gives you a measure of the V. You still need a measure of the E, so that's your Vane filter. These are called Vane filters, by the way, electricity. And then you follow it up with, in this case, a hemispherical electrostatic analyzer, CEM detect to do the detection. I haven't put a reference in here, sorry about that. That's your time of flight technique now. Here, again, particles coming through, electrostatic analysis, so you got the energy there, and this is where time of flight is performed. So let's zoom in a little bit here. Particle comes through, there's, in this case, a carbon foil, and as it punches through the foil, it generates secondary electrons. And these secondary electrons, there's an electrostatic mirror here. So with the right voltages, these then are deflected away and give you a start signal. The ion subsequently goes and hits another carbon foil or another detector or surface which generates more secondary electrons. And in this case, it's focused onto a different stop detector, and then the start and the stop give you the time of flight effectively. It gives you the time that it took for the particle to go from this position to that position. And this doesn't work for us on QB50 because our energy is so low. Typically, to punch through that foil, you need about 15 to 25 kilovolts acceleration, so it's much too complex. We are in such a low energy range that we can happily use electrostatic gating. And this is where I was saying you tune your instrument for a very specific science, and then you can achieve miniaturization relatively easily. Then there is the Fonema technique. Here, the E beam is parallel to the B field. And as you can see, in this case, the E beam is, let's say, the electrostatic force is bending the trajectories down, the magnetic force is bending it that way, and you end up with these so-called Thomson parabolas. And by putting a 2D position sensitive detector here, you simultaneously get energy and mass information, and a very powerful technique, not used so often because it is quite a complex realization, all these magnetic fields and so on. And here's a slightly more detail of the Fonema analyzer that was built for the Mars 96. Unfortunately, the rocket never made it to space, so we never got data back from this instrument. But what you can see is it's a really fantastic engineering marvel. If you go to the Science Museum in London, you will see that what it has is an electrostatic mirror here, which focuses particles from different angles to different positions on the 2D detector, and each of these has Thomson parabolas built into it to give you the energy mass. So you get that angle out of that electrostatic mirror, and that electrostatic mirror is of course 360 degrees. So when you have a whole bunch of these detectors in that plane, you're effectively covering an all sky. And it's fantastic combination of all the techniques that I've effectively talked about, but with two back-to-back, you get an all-sky mass and energy analysis simultaneously. Very powerful when you want very fast time cadence measurements and you want to make a full 3D of the sky in tens of milliseconds. And recently, almost most of the white papers that I've seen for plasma physics, they want very, very fast measurements. So these kinds of things are ideal, and lots of people are working on a slide close-up showing the hyperbolic electrostatic mirror. It was built by a bunch of collaborators from Russia, and it's amazing. But within there are your position-sensitive detectors and the magnets, etc. An example of a toroidal geometry, but in this case, there's a magnet here. So you got the energy analysis in there and a magnetic spectrograph, 2D position sensitive detector, and you get, again, pretty powerful combination of energy and mass. And when it comes to neutrals, as we are doing on the INMS, here's an example of a neutral particle analyzer. You ionize it, and then again, you can have magnetic fields and electrostatic fields to give you your energy and mass simultaneously. So a few examples here. Right, so what we talked about is electrostatic analyzers. When you do have species identification, sometimes, like on QB50, you can get away with very simple energy analysis because the spacecraft velocity is known, but otherwise you need to do more complex measurements like time of flight, and of course you can use magnetic fields and combinations. And of course these were the sort of examples that I talked about, a whole bunch of references. Thank you for listening.